Welcome to Math 150, Section 2, 2021, Lecture 19. So there was a malfunction in Section 1 and the recording did not happen. So we got to be game on today. So there is no margin for error. Otherwise, I have to give this lecture for a third time. And given how pleasant some of these integrals are, I just haven't been good enough to merit getting to do these integrals 3 times. So the first question I had for people was to just talk a little bit more about setting up some of the calculations. And again, it is hard to disguise when you want to use spherical coordinates. If you see a sphere, you should be thinking spherical coordinates. Whenever you see a circle, you should be thinking polar coordinates. I can give you tedious, painful calculations just to give you practice. But at the end of the day, we only care about this because we really want to apply it to a problem that matters. And one of the most important problems to apply this to is the attraction of two masses. In particular, say you have a body like the sun and you have a point particle, what is the force of the sun on the particle? And the great result that Newton had is that if you're outside the sun, you may assume that the sun has all of its mass at its center. And that greatly reduces the calculation you need to do. It is one of the most important integrals ever done in the history of science. If instead of having a solid sphere, if you had like a spherical shell and you were inside, there's actually no force on you if you're inside the shell. It's a really nice calculation. We will do the calculation and we'll just set it up on a sphere of radius r. So, without loss of generality, where should I assume my point masses? No. Can't be a 0, 0. It's going to be somewhere in space, and we'll assume it's outside the sphere. Where should I put it? Where would be a good place to put it? I'm sorry? Well, the point may not be on the surface. Hopefully, we're not calculating the attraction of the sun for a rocket on the sun. That rocket would just destroy itself immediately. So it can't be on, it has to be some distance off the surface. Where do you want to have it? Do you want to have it over here, up over here? It's nice to have it right above the North Pole.
What do you think? I'm sorry.
Just the second mass. We want to figure out what is the attraction of the sun on a point mass. We might as well put the point mass above the North Pole of the sun, because we want to have a little bit of a specialness in the z coordinate for spherical coordinates. And so it's just going to make the calculations a little bit easier. So there's a lot of ways you could do the calculation. You could assume you have a spherical shell and calculate the net force of the spherical shell. And if you show that that's equivalent as if all the mass is at the center, well, then you can just collapse and take a bunch of shells. We'll do the more general case of doing every single point in here. Now, there's a tremendous amount of symmetry. If I take a point over here, it's going to have a force. The force is along the line connecting the 2 points. There is a corresponding point on the other side over here, and so you see that the xy components will cancel. And you'll only be left with the z component down here. So I'm not going to do all the physics and write down the integrand that was done online. I'm just going to talk about setting things up. I'm only going to care about the z component. And so imagine I have some point on a sphere of radius rho. And again, I have the largest circle of radius r. But I have some point of radius rho, and I want to calculate the contribution from this point over here for the force. So if this is rho, I'll call this little r, and this over here is fixed. I'm going to call that h, the height above the center of the sphere. And we'll always have that as h. I need to calculate what this angle is to figure out what component of this force is in this direction. Any idea how we could get that angle? I'm not going to do it, but any idea what formula we could use to find that angle? Law of cosine. And I'm going to call it angle C, law of cosine. Why wouldn't I use theta? We always like to use theta for angles. Why am I using C? Yeah, we're using theta for the spherical coordinates, and we're using phi for the spherical coordinates. So I have to use C.
Why is R like the bigger circle?
Oh, because I'm assuming we have a sphere of radius capital R, and then we're on a smaller sphere inside of it, a radius rho.
Okay.
So little rho is going to range from what to what? From 0 to big R. You could do this as a two-dimensional problem and say, let's just calculate the force from a spherical shell of radius rho. I'm going to let rho vary because we've set up the volume integrals with dx, dy, dz transforming. So imagine I have to get every point on the sphere and inside the sphere as well. So if I just had to do on the sphere, then rho would always be capital R. But I'm allowed to be inside the sphere as well.
So what's that little r?
The little r is the distance from my fixed point to the point whose mass I'm trying to calculate the contribution. And I have this point range over the entire sphere, inside and out. So this point could start all the way down at the south pole and go all the way up to the north pole. What's going to be the range for theta and what's going to be the range for phi? So what's theta go from?
0 to 2 pi.
0 to 2 pi. And what does phi go from? So phi starts off at 0, goes all the way down to pi, and then that's it. Because once it goes down, then you just spin around theta from 0 to 2 pi, and you get everything. So phi is just going to go from 0 to pi. Let's try to write this down in Cartesian coordinates. And this is the advantage of having done section 1 is, I am now aware of just how bad it's going to be. And I have my integrand f of x, y, z, dx, dy, and z. What is the smallest value z could be? How small could z be? Negative R. We have a sphere of radius capital R. So the smallest z could be is all the way down here at negative R. And the largest can be as R. Now we have x squared plus y squared plus z squared is equal to r squared when we're on the surface of the sphere. And so we want to figure out what is the maximum range for y. What is the maximum range for y given our value of z? Well, so we could be inside. So it could be x squared plus y squared plus z squared is less than or equal to r squared. I don't have to be on the surface of the sphere of radius r. I could be inside. So I get y squared is less than or equal to r squared minus z squared minus x squared. If I wanted to make this as large as possible, I would take the equality, and what would I take for x? 0. If I wanted to make y as small as possible, I would take the equality, and I would still take x equals 0, and I would take the negative square root. So I get y goes from negative square root of r squared minus x squared, and so r squared minus z squared, to square root of r squared minus z squared.
Why did we take that way? Or why did we make that 0?
Well, I want to make this as large as possible. What's the range for y, the given value of z? The best I can do is having x be 0. And now when I look at what's left over for x, I get x goes from negative square root of r squared minus z squared minus y squared to r squared minus z squared minus y squared. And nobody should want to do anything with this integral. So we want to convert things. Well, we have to figure out what is f of x, y, z. Well, remember, x is rho sine phi cosine theta. Y is rho sine phi sine theta. and Z is rho cosine phi. And this is because we're coming down like this, here's phi. This is going to be rho cosine phi. This is rho sine phi, and that's r from your polar coordinates now. So what I would do is I would replace the f of x, y, z with f of rho sine phi cosine theta, rho sine phi sine theta, rho cosine phi. Hopefully, your integrand only depends on x squared plus y squared plus z squared. If it only depends on x squared plus y squared plus z squared, in spherical coordinates, what is x squared plus y squared plus z squared? Rho squared. And so now in spherical, I would have f of rho sine phi cosine theta crap, right, whatever the other two things are. Then I have my volume element, rho squared sine phi d rho d theta d phi. And that's how dx dy dz transforms. And we talked a little bit about why this is true for polar coordinates. Why does dx dy become r dr d theta? And we knew it has to have at least an r, because d theta is not a length. Dx dy is meters squared as an area. R dr d theta is just a length, it's just meters. Similarly, d rho d theta d phi, that has length, units of length, it's just meters. I need a rho squared to make it correct. Now, the sine of phi is much harder. The best way to see where the sine of phi comes from is we're using polar coordinates, and the radius is effectively reduced. It's not rho, it's rho sine phi, because now we're going in your circle above the xy plane. This is not a proof, but this shows you why it's reasonable that we have a sine of phi coming in, because when we go to do polar coordinates, we're not using rho as the radius, we're using r equals rho sine phi. The radius was reduced. And since we had r dr d theta, the r is now rho sine phi. And that's where the sine phi is coming from. It's also nice to note that sine phi is never negative in this range, which is good. You should never be getting a negative value for the change. All right, now we have to figure out the bounds. So the first is we integrate from rho. So rho goes from 0 capital R, then comes theta, goes from 0 to 2 pi, and then phi goes from 0 to pi. And we're integrating over a nice box. And that's much better than integrating over a sphere where the bounds of integration depend on the others, which is not surprising that the bounds on the first one depend on the fixed values of the other two. Depending on what I fix them to be, that's going to impact what goes on there. I may have a small mistake in here. I don't care, because I would never do this integration. Right? When you see all those square roots and the bounds depending on the bounds, you shouldn't do this. As soon as you see a sphere, you should be thinking, how can I make this a spherical integral? And you just have to remember, I have to transform my function. And I have to transform the volume element dx dy dz to rho squared sine phi d rho d theta d phi. And now we just substitute everything in, and now we just have 3, hopefully, independent Calc 2 integrals. That hopefully the integrand splits as a function of rho times a function of theta times a function of phi. And if that's the case, then I can just integrate them all one at a time. If they depend on each other, then it becomes a little bit more complicated. To finish the problem, you would have to do some physics and figure out what is the z component of the force from here. As much as I love physics, I don't want to get into that calculation today. I want to spend today trying to review some Calc 1, Calc 2. The big lie or the misleading concept from Calc 2 that you often have when you finish the course is you feel that you have learned how to integrate. You haven't. You have learned how to integrate a very small sliver of special functions. Fortunately, those special functions describe a lot of things in the real world. So it's not terrible. But most functions do not have a nice closed form for the antiderivative. Or if they do, it is a bit of a stretch to find. So I will give you 2 extra credit problems at the end of today to find closed form antiderivatives without using Mathematica, Wolfram tables of integrals, the internet, just to see if you can do them with pen and paper. Okay. So what I want to do now is I want to review some concepts from Calc 2 and use this as a way to review some of the stuff we've done in Calc 3. Most of the time in our class, we use very little multivariable calculus. We do multivariable calculus for a small amount of time to set up a problem, and then we pray that it reduces to a Calc 1 or Calc 2 problem, or what I think we would hate but will accept, an algebra problem. So what I want to do is I want to talk about lengths of curves. So here is a strange fact. If I give you 2 points, and let's say I travel from this point to this point by always moving to the right hand. Okay, so I'm never moving leftward, I'm never moving down. I claim that any 2 paths have the same length that connect these 2 points. Does anybody believe that this is reasonable, or is anybody suspicious that any 2 paths connecting them have the same length? So this straight line has the same length as the front. And I will prove that to you right now. You ready? All right. So we've learned in calculus that we want to approximate things, divide up into small little pieces and then add them all together. So I'm going to divide into lots of small little pieces. Okay? And for each one of these, I'm going to replace the little curve by moving right and up, 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 right and up. These are all going to be very small increases. So if you zoom in on one of them, it's going to look like that. I'm going to approximate that curve by the horizontal distance and the vertical distance. And if you look at it, do you agree that when we zoom in really close, that these are almost the same size? And now what we do is we just add them all up. So let's add up all the horizontal pieces. Well, I can drop all the horizontal pieces down, it just becomes the line segment over here. I can take all the vertical pieces, push them to the right. So any curve has length that's equal to the distance from here to here, plus the distance from here to here. Well, by Pythagoras, we know that this is equal to the sum of the squares of these 2 square rooted. What the hell is going on? If I tell you that I have done a calculation and we're off by $1 million, good or bad? Good! It depends. Let's say we're talking about the US GDP, and I have predicted the GDP to within $1 million. Good or bad? No, come on. I want a little bit more than that's good. Right, that is miraculous. Right? If I'm within $1 million of the US GDP, I believe that I've been given the number that's going to be released in advance. And I'm putting in a small little error, so I'm not caught. I would be suspicious of any prediction within $1 million. The US GDP is on the order of trillions of dollars a year. What if I say we're talking about how much you and your family will owe for your Williams education, and we're off by $1 million? And you can figure out which way we're going to be off. Significant. Okay? So the same magnitude can be insignificant or tremendous depending on what it's relative to. If I look at the size of the error is small, but it's on the same scale as the size of the segment. And because I have so many of them adding, a small little error of size 1 over n, if I add it n times, becomes significant. So I should not be approximating the length of that curve by horizontal plus vertical. How should I approximate the length of the curve? Not horizontal plus vertical, but hypotenuse. Excellent. So I should draw a hypotenuse connecting them. And as I do a smaller and smaller region, that should be better and better. How many of you have actually done lengths of curves in high school or Calc 140? It's usually not covered because the integrations become so painful. but I want you guys to see it. And again, it's a good way to review some of the material before our exam. It's a good way to review integration techniques while seeing something worth seeing. So let's imagine we have some curve in space. C of t, which is x of t, y of t, z of t. Although, of course, if we're in the plane, z of t might just be constant, or we might not even have a component. And the way it works is I have some interval here. Usually goes either from 0 to 1 or maybe 0 to pi. And for a given value of t, I map and I get some point c of t. And then what I'm going to do is I'll take a bunch of points and I'll approximate the length of the curve by connecting those points. Yeah. So if you've ever played those connect the dot games, do you agree that as we take a more and more refined partition, this should be better and better, at least if the curve is nice and smooth? So imagine this is the point t sub k, and this is the point tk plus 1. So these are vectors. These are points in three-dimensional space in the order. How would I calculate that length? Well, how would I at least find the length? You can subtract the two vectors. And if I subtract the two vectors, I would get c of t k plus 1 minus c of t k. And then how do you find the length of a vector? Length of a vector, right? So you just want to find its length. Well, what I'm going to do is I'm going to rewrite this as c of t of k plus 1 minus c of tk. I'm going to divide by delta t. I'm going to multiply by delta t. So I'm going to chop this up. This is k, this is k plus 1, and that distance is delta t. So I can divide and multiply by the same thing. Why might I be doing this? Is this looking like anything you might know? What is it looking like?
Definition of the
Definition of the derivative of c of t. So it should be the limit as my partition goes to infinity. The sum k goes from 0 to n minus 1. The length of c prime of tk. And so as I do the limit, this is just my standard calc 1. This just becomes the integral from 0 to 1 of the length of c prime of t. And that will be the length of the curve from t equals 0 to t equals 1. Okay? Whenever I give you a formula, what should you do? See if it makes sense. So I need an example of a curve that makes sense. What is the simplest curve you can think of where you can calculate its length? A line. So let's test with a line. Now, before we do the test, if it fails the test, what does that mean? I did something wrong, either in the test or in the theoretical derivation. So we know going into this, if the test fails, something's wrong. What if it passes the test? Are we confident that this is a correct? Why not? It's good for lines, and you know, a line is really simple.
Well, it's good for that one.
Yeah, it's good for that one. This reminds me of the joke about Scottish sheep, which if people want, I will say after class. So it works for lines. Maybe it only works for lines. Maybe lines are too simple. When we did the fundamental thing of calculus, the first couple of things we tested, oh, good, it gives the area of a rectangle. Oh, it gives the area of a triangle. It wasn't until we went later that we actually had a test that we liked. Oh, let's choose the following line. Here's the point 0, 0. Here's the point 1, comma, n. And I'll calculate the length from here to here. So this is a nice line. I've chosen it to have slope m, and your m is free. Okay. Can anybody tell me what the length of that line is? What's the length of this line from 0, 0 to 1m? Yeah, square root of 1 plus m squared, because this is 1, and that's m. I chose the right triangle. So we need to write down a parameterization for c of t. So it's x of t, y of t. Well, if I choose x of t to just be t, what would y of t be? So we're trying to write down the equation of a line of slope m, going through the point 0, 0. So if x is t, what would the corresponding value of y be? T times m, or t. We could do it another way. It's the point 0, 0 plus t times the slope vector. Remember, we spent all this time at the start of the semester. What would be the slope vector here? One comma m, and you see it just reproduces what we had in one. So both ways give us the same curve. C of t is t comma mt. Typically, but not always, you start off by saying, let's let x of t be t. Let's make that part simple, and then figure out what the corresponding y is. So now we need to calculate c prime of t. So if c of t is t comma mt, what's c prime? 1 comma m. So what would be the length of c prime of t? It would just be the square root of the sum of the squares. So it would just be the square root of 1 plus m squared. And so now to calculate the length, we get the length to be the integral from 0 to 1 of the square root of 1 plus m squared dt. Oh, this is a really nice integral. Does the square root of 1 plus m squared have any t dependence? It's a constant. So you can just pull the constant out of the integral, and it's just the square root of 1 plus m squared times the integral from 0 to 1 dt. If you were to ask, we asked 100 math professors what's the easiest integral they can give their students, top 5 answers are on the board. This would be on the board. Right? I think only one integral beats it. What integral would beat that for easiness?
0.
Yeah, integrating 0 dt. And so you just get 1, which is the square root of 1 plus m squared. Yay, it works. But again, we're not that confident. A line is not a truly general curve. A line is extremely nice. I gave you 16 divided by 64 in this class, right? And we saw 16 over 64 is 1/4, 19 over 95 is 1/5, 49 over 98 is 1/2, but 12 over 24 is not 1/4. Just because something works a few times does not mean it always works. So you have to be careful. So we need another curve. So who wants to throw me a curve? And a good one.
I'm expert.
Okay. We will do that later. Because it's a fine curve for you to give me, but do you know what the length of the parabola is?
No.
So I agree completely that that's the next curve we should look at. The next curve we look at should absolutely be the parabola. The problem is we don't know the length of a parabola. So if I give you an answer, how can you tell if it's right? So do you know any other curves where you know the length of the curve? Circle. So let's do a circle. We'll do a circle of radius 1. You could easily modify this for anything. squared plus y squared equals 1. So we have to think, how should we parameterize this? We want to come up with a curve C of t is x of t, y of t. And there are several ways to do this. We could integrate over the entire circle, or we could integrate just over a quarter circle and multiply by 4. Right? Either way is fine. So I need to parameterize x of t, y of t. Any thoughts on how I should do this? I'm sorry? Polar coordinates. You should have a Pavlovian response. Whenever you see a circle, what should you be thinking? Polar coordinates. It may not be the best thing to try, but it should be something that's worth trying. So if we were to do polar coordinates, in polar, x would be r cosine theta, y would be r sine theta. Oh, okay, so here r is just going to be 1, and then theta is basically going to be rt. So we could try cosine t sine of t. And what would be the range of t if we want to get the whole circle? So when t equals 0, we start off at the point cosine 0, sine 0, which is right here. When t equals pi halves, we get up to here, 2 pi. So 0 less than equal to t less equal to 2 pi. We need to compute c prime. So what would c prime of t equal? So negative sine of t. And now we want the length of c prime of t. So it's the square root of negative sine squared plus cosine squared. Ooh, what's sine squared plus cosine squared? It just equals 1. So we get that the length is the integral from 0 to 2 pi of 1 dt. Whoops. And this is a non-trivial example. We need to know the length of a circle in its circumference. But if we know that, this is now a real test of the formula we just derived. There is another way to do this. We could do C of t is t comma y. So if I choose t for x, what would y be? Almost.
1 minus t.
1 minus t squared. Right? Because x squared plus y squared equals 1, so y squared is 1 minus x squared. So if I tell you x equals t, y is the square root of 1 minus t. And here, I want to be careful because I could also, of course, go down. So I'm going to say 0 less equal to t less equal to 1. Oh, sorry, not 1. I have. No, I want 1. Okay, so now we need to calculate c prime. You do 1, I do 1. Which one do you guys want to do? So we'll leave the other one for me. So we have the square root of 1 minus t squared. So it's 1 minus t squared to the 1/2. It's going to be 1/2, 1 minus t squared to the negative 1/2, and then negative 2t. The 1/2 cancels with the negative with a 2. And now when I square things, the negative sign will cancel. And so I will get the length of c prime of t is the square root of 1 plus, when I square this, I'm going to get a t squared up top. And then down below, I'm going to get 1 minus t squared to the negative 1. So that's squared root. So it's 1 minus t squared. So what's 1 plus t squared over 1 minus t squared? How do we handle that? Yeah, common denominator. I multiply this by 1 minus t squared over 1 minus t squared. We get 1 minus t squared plus t squared. Oh, that's not so bad. We get the square root of 1 over 1 minus t squared, which is just 1 divided by the square root of 1 minus t squared. So I now have the length is 4 times the integral t goes from 0 to 1 of 1 over the square root of 1 minus t squared dt. At this point, you should really appreciate polar coordinates. Yes?
Where's the 4 come from?
Because I'm only doing a quarter of the circle, so I have to multiply by 4. Okay, who remembers the, I think, inverse trig functions maybe? I don't know. The antiderivative of 1 over square root of 1 minus t squared. Maybe it's not inverse trig functions. One way to do this probably is to find what function has derivative 1 over the square root of 1 minus t squared. Another is to do a technique I said we're probably not going to do too much in this class. And one that I won't have you have to do on exams. What technique would we use for this integration? Anybody remember? It's not integration by parts.
By holes.
No.
Oh, fraction,
I'm sorry?
like, partial fraction.
Not partial fractions. It is related to U substitution. Calling it U substitution is not wrong, but it has a special name. It's a special type of U substitution. Trig substitution. I've got a 1 minus t squared. You should be thinking 1 minus cosine squared or 1 minus sine squared would be 1 minus cosine squared is sine squared, 1 minus sine squared is cosine squared. When you take the square root, it becomes nice. So I want to choose t to either be sine or cosine. Because I go from 0 to 1, I'm actually going to choose t to be, I'm sorry. Yeah, I'm going to choose t to be sine of theta. And as t goes from 0 to 1, when t is 0, theta is 0. When t is 1, theta is pi half. I could have taken t equals cosine theta, but then I would have things going backwards. It doesn't matter. I just prefer it this way. So now, 1 minus t squared square root is the same as the square root of 1 minus sine squared theta. What's the square root of 1 minus sine squared? Cosine theta. And the last thing I need to know is if t equals sine of theta, dt derivative of sine is cosine theta d theta. So putting everything together, you get the length is 4 times the integral. Theta goes from 0 to pi half. Now we have 1 over square root of 1 minus t squared, that becomes 1 over cosine theta. I'm a little worried with the cosine theta in the denominator until I see that I multiply by cosine theta d theta, and the thetas cancel, and this is just 4 integral from 0 to pi halves of dt. And what is that integral equal? 2 pi. So it works. And what's nice is we were able to do this without actually computing the antiderivative of 1 over the square root of 1 minus t squared. Because we had a nice copy of how many times that happened, we would embrace it. Okay, any questions on this? Over here? Oh, yes, it should be d theta. Thank you. Well, actually, I could easily turn the theta, t into a theta. Yes, it should be d theta. So again, more evidence that our formula is correct. It was a good way to review some of your Calc 2. It was a good way to review some of the Calc 3 of just vectors and differences. And you can see that if you choose the wrong way to look at things, is it wrong? Well, it depends. We still got the answer. So I'm not going to get into a philosophical argument as to is it wrong. It's more work than necessary. Two of my friends took a year off of college to help the amazing James Randi set up his institute to debunk psychics. And the amazing James Randi was often sued by somebody who claimed that he did have psychic powers. And so eventually, the amazing James Randi had to say things such as, if he's doing this using psychic powers, he's doing it the hard way. And you know, I can also bend a spoon with my mind. And so it's not wrong to do it without polar coordinates. And I said to you, most of the time, you know, you'll take x of t to be t, and then you figure out what y is. This is one of those times when that's not a good idea. All right. Any questions about this problem? All right. So we have one item left. So it was the suggestion that the next curve we should look at should be y equals x. Y equals x squared. Because, you know, we did this when we tested the fundamental theorem of calculus. The first thing we did was straight lines, and then after the sixth test we moved on to parabolas. And we were able to show by using a formula, you know, for sums of squares, you know, the sum of the first m squares is m times m plus 1 times 2m plus 1 over 6. Using that, we were able to prove that it worked. So the question is, can we do something similar here? Unfortunately, most line calculations, most lengths of curves cannot be found. If you want to calculate the length of an ellipse, we did that in the video, it's painful. The area of the ellipse is actually immediate from the area of a circle, but the length is much, much harder. So let's try y equals x squared. So here's a parabola, here's 0, here's 1. So we need c of t. So you give me a value of t, what would the corresponding value of y be? So it's x of t, y of t. If x of t is t, what's the value of y of t? T squared. Okay, t squared, is that a nice function? Doesn't look so bad. Let's calculate its derivative. C prime of t is what?
1.
It's 1 to t. And so the length of c prime of t is the square root of 1 plus 4t squared. So the length is going to be the integral from 0 to 1 of the square root of 1 plus 4t squared dt. We can make things a little bit nicer. I'll let u equal 2t. So as t goes from 0 to 1, u goes from 1 to 1. 0 to 2. And if u equals 2t, du is 2 dt, or dt equals 1/2 du. And you can see now why I wanted to do problems like this in class today. This is a great way to review integration, but doing it in a way that we actually get results that might matter. I have a dt that I want to solve for, and so I don't want du equals 2 dt. I want dt equals 1/2 du to make things as easy as possible. So the length is just integral from 0 to 1, and I have the square root of 1 plus u squared 1/2 u. So it's 1/2 the integral from 0 to 1, square root of 1 plus u squared u. Okay, who remembers what function has derivative square root of 1 plus u squared? This can be done. And so this is the first extra fact. Find the antiderivative. Now, unfortunately, we will not be able to do the trick we've done in the past. In the past, what have we done? We did these wonderful tricks. And we said, well, we want to create cosine squared from 0 to pi, halves, That's the same as half of the integral from 0 to pi. That's the same as a fourth of the integral from 0 to 2 pi. And the integral of cosine squared is the same as the integral of sine squared. So it's going to be 1/8 of the integral of cosine squared plus sine squared. And what's cosine squared plus sine squared? 100. So for a lot of problems, we don't need to know the antiderivative if we're integrating it over a nice region. Unfortunately, there's no nice region here because instead of finding the area under the parabola from the length of the parabola from 0 to 1, I could ask you the length from 0 to 2 or 0 to pi or 0 to 17e. You're not going to be able to do a trick like that. You need to find the antiderivative of the square root of 1 plus u squared. And so I will give you one other extra credit problem. Choose alpha beta greater than 1 such that y to the alpha equals x to the beta has a nice length integral. And I'll make this extra credit. And what am I not going to allow you to choose for alpha and beta? 1. Or more generally, what will you tell me I'm not going to allow you to do for alpha and beta? Alpha and beta cannot be equal. Because if alpha equals beta, what do I really have? I have y equals x. I just dressed it up fancy. So I want alpha not equal beta. Because if alpha equals beta, it's not fine. So can you find an alpha and a beta where we can actually calculate the length of that curve nicely? And that means the integral that arises is an integral that we can do. How many of you remember those images in polar coordinates like lemmisates and all those in the cardioids? So it might be the fact that I'm asking for y to the alpha equals x to the beta is too limiting. But there might be some polynomial in x and y equals 0. Maybe that has a nice closed form for the length. I don't know. Yes.
Since we went from t to u, would the integral go from 0 to 2?
Oh, yes, it should go from 0 to 2. Thank you. Yes. Because we changed the bound. So I wrote everything down, but then I still substituted it. Yes. And the reason is 1 plus u squared actually has a nicer antiderivative. And this is a dead skill. Has anybody here other than myself ever used a table of integrals? Okay. Once.
Yeah.
More than once or?
Twice.
Twice, okay. I will try to remember. I actually have, from I think high school, I still have it, a piece of paper with standard antiderivatives. And I have kept it for years. It's one of the few things I've really saved from high school. And part of learning how to do calculus was to learn how to convert from what you were given to what you actually had in your books or whatnot. And it was often a little bit of a challenge as to how do I do this. You probably would not find in the table of integrals the integral of the square root of 1 plus 4t squared, because you can do a simple change of variables and reduce it to 1 plus u squared. And so rather than having all of the stuff caught in your table of integrals, you would only have a few smaller items. All right, so this is a good place to stop.